This is Basic Chemistry by Timberlake, section 5.6 on periodic trends of the elements. So if something's periodic, it's repeatable. If the element table is periodic, then the element table is going to be repeating certain characteristics or there's going to be certain trends that you can predict simply by looking at the periodic table. Where is it in the period? If something happens at the beginning of a period, they're going to be similar to other things that happen at the beginning of a period, no matter what period that is. If something is at the end, so depending upon where an electron is, you can make certain guesses as to how, if we're talking about the very last electron placed, you can make certain guesses as to all kinds of things, whether it's easy or hard to steal an electron, or give an electron, whether it, talking about how big an atom is, or its ion. So all of these we're going to look at one at a time, and we're going to continuously look back at the periodic table to see if it helps us to make some idea. So let me remind you that valence electrons are the outer electrons, and there are only 8 of them generally. Period 1 is the exception. There's 2. The rest of the periods have 8, and they are made up of the S's and the P's. So when you add to 8, the S, remember, has 1 orbital in it, so that's 2, and the P has 3 orbitals in it, so that's 2, 4, 6. 2 plus 6 is 8. So to get to the magic number of 8, you are looking at your S orbitals, or your S subshell, and your P subshell together. That's why that the D subshell is actually inside. Remember I said that it's one off. Instead of being in, it looks like it's in row 4, but the shell, it's actually in shell 3. It doesn't count towards the chemistry. Remember, the valence chemistry, whether or not something shares electrons or whether something steals electrons, is based upon the outer number of electrons, the valence shell. So it determines the properties. Remember, everything in that column is going to behave the same way chemically. Well, that means the very last valence electron is what that column has in common. So for instance, they're giving an example here of phosphorus. Phosphorus has 5 valence electrons. Well, everything in its column also has 5. So for that reason, there's a trend periodically. You can make some guesses about certain traits just based upon how many valence electrons that a certain column has. Okay, so for instance, let's look at just group 2 electrons. The electron configuration of beryllium ends with 2s2. Magnesium ends with 3s2. Calcium with 4s2. Strontium with 5s2. Since they have similar numbers of valence electrons, we're going to see that they have a similar chemistry. Often, chemistry is based primarily on the number of valence electrons that can interact with the other valence electrons. The electrons will either join together and share, or they will steal from each other and become ionic, and that's how you form bonds. So that's why chemically anything in a group will behave similarly. Okay, so here is a kind of a simplified periodic table where all of the D subshell is gone and all of the F subshell is gone. So we're only looking at groups 1 and 2, lithium and beryllium. Then you skip that whole valley in the middle. You've kind of pulled it out. Then you have the last 6, boron through neon. And remember, helium is positioned in the group 8 because it has a full subshell, and so it behaves like a noble gas. But you could have equally put helium above beryllium because the S subshell is filled. So let's do a quick review. State the number of valence electrons for each. Okay, so if oxygen is in group 6, then it must be 6. If aluminum is in group 3, it must be 3. If chlorine is in group 7, it must be 7. So looking at the periodic table could instantly give you these answers. Here's another one. State the number of valence electrons for each. Well, calcium is in row 2, so it's 2. Okay. Group 6A. Well, I don't even know what elements are in group 6A, but remember 6A is 6 valence electrons. It's the periodic table in our room is 16, but remember we're skipping all the D's, so that's 10 out. So the number 16 would drop down to the number 6, and there would be 6 valence electrons. Okay. 10. Let's go back quickly so you can see it. I need just a minute. Let me find a periodic table. I'll jump up a bit. Okay. All right. So you just need to see that 10 here is in the 4. So that means it'll be 4 in its outer shell. You would have to see the periodic table. Okay, it would have 4. All right, let's go on. This is called a Lewis-Dot structure. Your book calls it an electron-dot symbol, but a Lewis-dot is the simplest way of explaining how many valence electrons you have. If you're wanting 8, okay, then you're going to basically put 2 to the east, 2 to the west, 2 to the north, 2 to the south. And you're looking for the column that a symbol is in. So in this case, magnesium. Magnesium has 2, it's in group 2. So you are going to put 2 electrons, or 2 dots, around that magnesium. That magnesium then, just in your mind, you can see, oh, it needs to connect either by getting stolen from. 2 of these are going to steal, or one of them is going to steal and the other's not, or something like that. Or you're going to share it in such a way that you can get 8. It's a very quick way of saying, how does this work in terms of getting 8? Are you going to share to get 8? How would you do that? Are you going to steal to get 8? Which ones would be stolen? Okay, so Lewis-Dot structures, you're going to see that I'm going to use them a lot in future classes. So when you write an electron-dot structure, okay, you're simply going to put the number of dots around that element symbol equal to the column that it's in, to the number of valence electrons. So sodium, for instance, is in group 1. There would be 1 dot. Magnesium's in group 2. There's 2 dots. Aluminum's in group 3. There would be 3. I think I've got my dots dumb right there. There would be 3 around aluminum, and the last 2 dots that you see above aluminum actually go above carbon. Carbon's in group 4. There would be 4 dots around it. Phosphorus would have 5. Oxygen would have 6. Why? Because they are in group 5 and 6. That's the way it works. Okay. So everything in group 2 would have 2 valence electrons, so they're going to have 2 Lewis dots. All right. So just an example, here's group 1. They all have 1 Lewis dot. Here's group 2. They all have 2. Lewis 3, they all have 3. Yep, this is pretty simple. Lewis 4, they all have 4, etc., all the way to 8. Okay, and believe it or not, as simple as this is, it's so useful. So let's do an example. So here is your generic electron dot. So we've got 1 dot. Which one of these would only get 1 dot? This 3 is in 3. 2 is in 1, 1 is in 1. Okay, so if sodium is in group 1 and it needs 1 dot, sodium would have 1 dot. Potassium's in group 1, it would have 1 dot. Aluminum's in group 3, it does not have 1 dot. Okay, what about this one? 1, 2, 3, 4, 5. All right, so I'm looking for one that's in 5. All right, so let's go back to the periodic table if we can find one. So nitrogen, phosphorus, and boron. Okay, nitrogen's in group 5. Okay, phosphorus is in group 5. Boron's in group 3. All right, so you'll see that, so boron could not have this structure. Nitrogen would, and phosphorus would. So your first trend is towards atomic radius. What you're going to see is that as you go across a row, the nucleus is going to pull harder and harder and harder on the electrons. Okay, and as it does, the size of that atom is going to go down. So as you go to the right, as you go from left to right across a period, the more it has, the more it pulls. Okay, it pulls it in. So for instance, if you get all the way to group 8, it's going to be very, very small compared to anything on the left. All right, but as you go down, they're going to get bigger. Why? Every time you go down another row, you are making a new shell of electrons on the outside. So it's like a nested group of electrons, shell, outside shell, with inside and outside shells. Every time you add one, you're going to add another shell, and that's going to increase the size. So the atomic radius gets bigger as you go down towards francium, and bigger as you go to the left towards the group 1 metals. So I would always think of it as that it is an arrow pointing down towards francium. The size gets bigger towards the lower left corner of the periodic table. Okay, so it increases as it goes farther down, because you're going to have more than one shell. Okay, it decreases as it goes from left to right, and as more protons increase the nuclear attraction for the valence electrons. So the valence electrons are a certain distance from the nucleus, but the nucleus is going to have more and more, as you go across, there's going to be more and more positives in the nucleus. Okay, but the valence electrons are the same distance. So that means that they're going to have a higher tug, and as you go across the row, it gets smaller and smaller and smaller. Okay, so which one is bigger? Lithium or potassium? Okay, well, they're both in group 1. Lithium is higher, potassium is lower. Potassium has more shells, so potassium would have a bigger atomic radius. Okay, how about potassium or bromine? Potassium's in group 1, bromine's in group 7 in the same row. So therefore, potassium would be bigger, bromine would be smaller. Okay, and then how about phosphorus or chlorine? Phosphorus is to the left, chlorine is to the right. So phosphorus would be bigger, chlorine would be smaller. Okay. Ionization energy. Make sure you're taking notes on this. Ionization energy is how easy is it to steal an electron. Okay. Is it easy to take candy from a baby? Well, then candy gets taken from babies if it's easy. Okay, is it hard to do it? Am I going to steal gold from Fort Knox? Probably not. Okay, it's probably harder than I think, and because of that, I don't do it very often. So ionization energy means a particular electron, is it easy to steal or is it hard to steal? By easy and hard, I mean how much energy does it take for me to remove that? If it takes a ton of energy, it usually doesn't happen. If it takes just a little bit of energy, then it probably happens a lot. Okay, so let's look here. If I have a group 1, which means that here's an inner size, and then this is the outer valence electron. I have one electron here. This is easy to steal. It's far away from the nucleus, and it's out there by itself. There's just one out there. That's easy to steal. Okay, and also remember, group 1 is large. It's farther away from the nucleus. So picking it off would be not such a bad, it would be easy. What if you have, this is groups, okay, if I remove it, then essentially I don't have a last shell, and my new shell becomes the inner shell, right? So for instance, let's say this is sodium, it is. Sodium, if I were to take one off, then sodium is still sodium, but it's an ion. It's one less electron. And so it has the configuration of the previous row's noble gas, which is very stable. So Na plus 1 right here is very stable. So a sodium ion is very stable. You're going to see it millions and millions of sodium compounds because it's so easy to take its electron that sodium becomes a sodium ion very, very easily because the electron's so cheap to steal. Well, that means that as you go across, it gets more and more and more expensive. Imagine that towards the noble gas, the nucleus is holding onto their valence electrons very, very, very tight. Well, it becomes harder and harder to steal. So it might cost $5 to steal something from group 1, but $800 to steal it from group 8. Okay, it's very, very hard, and so you don't see it very often. It's easier to steal something from the left side of the periodic table and make it become a positive than it is to steal from the right and make it become a positive. You never see positive chlorine, but you often see positive sodium for that reason. So what about this? Select which one has the higher ionization energy. Which one's easier to steal? Okay, well, I never mentioned this. Lithium and potassium. Lithium is closer to the nucleus. Potassium is farther away from the nucleus. Which would be easier to steal? Something right in the front door of the police station, or something way off in the middle of the woods? Okay, the closer it is to the nucleus, the more pull it is from the nucleus, the harder it is to steal. So as you go down the periodic table, it's easier and easier to steal it. Okay, as you go to the left, it's easier to steal, and as you go down, it's easier to steal. So the higher ionization number is harder to steal. So the higher ionization number on the periodic table would tend towards pointing, say, to fluorine. It's harder to steal because it's closer and harder to steal because it's farther to the right. So which one has the higher ionization energy? Lithium. Which one would have the higher ionization energy? Potassium. No, wait. Bromine. Which one's harder to steal? Higher ionization energy is harder to steal. Which one's harder to steal? Lithium. Which one's harder to steal? Bromine. Which one is harder to steal? Potassium or chlorine? Okay. Well, that's on the same row, so it's a little bit harder, but you're going to say towards the right is higher ionization energy, and towards the top. So towards fluorine is going to have the higher ionization. So I would say chlorine here. Okay. Sizes of the ions. A positive ion, okay, so it's lost an electron. So if it's lost an electron, it's usually lost an entire row, entire shell. So the ions are going to be smaller than the atoms. If you had lithium and you lost that last electron, you lost that whole shell, and so the size of that ion is smaller than the size of the atom. Okay? So the sodium ion forms when the atom loses an electron. That means the whole shell is gone. So here is sodium, and it was this big, okay, because there was a third shell. But if I steal that electron, there's no third shell anymore. That means it's only the size is the same as if it were neon, the size of the noble gas in group 2. That means it's smaller. So ions, positive ions, are usually smaller than the atom. Okay. How about the negative? All right. A negative ion, in order, usually you steal until you have group 8. So you're going to see that it's going to get bigger because you're essentially adding more to the cloud. You're adding more electrons to the cloud, and so the ions will be bigger. So a negative ion is bigger than the atom. A positive ion is going to be smaller than the atom. Okay. All right, that's as far as we're going to go in this chapter. I hope that you don't have too serious of a headache.